Talk about linear transformations. You're going to see that multiplication by a matrix A transforms a vector X into a new vector B. Okay, so A is this 2 by 3 matrix, and we're going to define T to be a transformation that takes X to AX. Or using the function notation that you're more used to, T of X equals AX. So your inputs are vectors X and your outputs are A times X. So is T a linear transformation? We're going to talk about what a linear transformation is in a minute. But in the reading, you should have learned that matrix multiplication is always a linear transformation. So this is yes. Matrix transformations are always linear. What is the domain of T? What kind of X's can you put in? Where do they live? R what? 3. Yeah, because A is 2 by 3, right? So A is 2 by 3. So if you're going to multiply A times something, that something has to be 3 by 1, right? The inner dimensions have to match. So if A is 2 by 3, then X, the vector, has to be 3 by 1. So the domain, if X is a 3 by 1 vector, the domain is R3. You can plug in vectors from R3. What is the codomain? What do you get when you multiply a 2 by 3 times a 3 by 1? A 2 by 1. Yeah, the inner dimensions match, so you're allowed to multiply them, and the outer dimensions are the result. So the codomain is R2. So 2 by 3 times a 3 by 1 will give you a 2 by 1 vector. So your inputs are vectors in R3, your outputs are vectors in R2. So what is the image of 1, 1, 0 under the mapping? So I've given you an X. You just want to figure out what AX is. So T of 1, 1, 0. So the image is just a word, another word for output. So T of 1, 1, 0. That means A times 1, 1, 0. And A is 1, 0, 2, 4, 0, 0. Now, you can do this matrix multiplication 2 ways, right? You can either take each entry from the vector and use it as a weight on the corresponding column and then add it all up. Or you can do the take a row and multiply times the column, take the dot product. So I'm going to do it the second way. So I know that my result should be a 2 by 1. So I'm going to build my matrix. It should have 2 rows, 1 column. So I'm going to sort of put in my blanks here. 2 rows, 1 column, and then I'll fill in. If I multiply the first row of the matrix times the column, I should get the first row of the result. First row times the vector gives me the first row. So imagine taking your 1, 2, 0, rotate it 90 degrees, lay it on top of the 1, 1, 0, multiply the things that line up, and then add them all together. So you're going to have 1 times 1 plus 2 times 1 plus 0 times 0. And then you do the same thing with the second row, and that will give you the second row of your result. So we're going to have 0 times 1 plus 4 times 1 plus 0 times 0. And we get 1 plus 2 is 3, 4. So the image of 1, 1, 0 under the mapping T is 3, 4. When you plug in 1, 1, 0, you get 3, 4. Are there other vectors with the same image? So I'm saying, are there other vectors that I could multiply by this matrix? Some other vector, x1, x2, x3, that will also give me 3, 4 as my image. How would I solve that? Oh, yes. Yeah. Okay, so you just solved it in your head. You were just imagining the multiplication and saying, oh, I can build that as long as I have 1, 1, anything. Yeah. If you didn't just see that, how would you have solved this equation for x? Put it into an augmented matrix and row reduce. Yeah. So you would do 1, 0, 2, 4, 0, 0, augment with 3, 4. Row reduce it with technology. You get 1, 0, 0, 1, 0, 0, 1, 1. So this just says that x1 has to be 1, x2 has to be 1. It doesn't say x3, the x3 column tells me nothing, right? x3 is a free variable. x3 is free. So as long as you choose any vector that is 1, 1, anything, the result will be 3, 4. So the one I gave you was 1, 1, 0. I could have put anything in that third spot and I would still get 3, 4 as my output. All right, if I want to find a vector whose image is 1, 1, same thing. Set up an augmented matrix, 1, 0, 2, 4, 0, 0, augment with the image 1, 1, and row reduce. And I get 1, 0, 0, 1, 0, 0, 1 half, 1 fourth. So that would says x1 has to be a half, x2 has to be a fourth, x3 is free because there's no pivot in the x3 column. So images, vectors whose image is 1, 1 would look like a half, a fourth, and then anything, x3. All right, I'm asking you about the range here. Is 812 in the range of T? That's equivalent to saying, is there a vector whose image is 812? Okay. Can you produce 812 by plugging in some vector in R3 to get it? So it's similar to what I was asking before, but instead of saying, find a vector whose image is 1, 1, I'm asking, can you find a vector whose image is 812? So you set up your work the same way, 2, 4, 0, 0, 8, 12. And as long as this is consistent, then 8, 12 is in the range. I'm not asking you what x produces it, just can you produce it? So this augments to 1, 0, sorry, row reduces to 0, 1, 0, 2, 3. So the answer is yes, right? This is consistent, which means that there is a vector in R3 that produces 8, 12 as an output. In fact, there are lots of them. It would be 2, 3, anything. All right, so 8, 12 is in the range. If I wanted to describe the whole range, okay, I know the codomain is R2. I know that the things I produce, I plug in things in R3. The things that come out live in R2, right? But can you produce any vector in R2? Any vector in R2. So if I did this, I said 1, 0, 2, 4, 0, 0, some random vector in R2. Will this always be consistent? No matter what you put there for B1 and B2? Let me ask you this. What makes a matrix inconsistent? What is it that you're looking for when you do your row reducing? What are you looking for when you go, oh, I can stop, it's inconsistent? A pivot in the augment lane. Did you call it a lane? I like that. A pivot in the augment lane, yeah. So you're looking for zeros and then a number, right? So let's look at, I just did a whole bunch of these, right? If I was looking for inconsistent, I would be looking for this to be 0, 0, 0, then a number, right? But every time I row reduced, the coefficient part of the matrix was 1, 0, 0, 1, 0, 0, right? So that bottom row, both of my two rows always has a pivot in the x1 and the x2 position. So this is always going to row reduce to 1, 0, 0, 1, 0, 0, some stuff. I don't know. It'll be related to B1 and B2, right? But my first, the unaugmented part, just the coefficient part, is always going to row reduce to this. So no matter what the stuff is over here, this is never going to be inconsistent because you always have a pivot in each row. So this is, because this is always consistent, because there's a pivot in every row, that means that the range is all of R2. You can get all of R2 as outputs from the function t. All right, so the activities for this section are longish, so let's start them today, and whatever you don't finish, we'll pick up when we come back on Tuesday.